All right, hi again, everybody. I thought rather than waiting till tomorrow to find out that it's going to just crash on me again, I thought I'm just going to record this and then I will give you access to this YouTube video. So here's the question that I'm trying to solve, and like I said earlier today, this is the biggest question of the entire course. Right? We're not going to be doing anything bigger than this. So really kind of go through this with me step by step, and see if you can just kind of stay focused on what's going on here, because there's a lot going on. Right, so the chemical reaction that we're doing is trying to make aspirin. Okay? And when I get you here in school, I might actually get you to make aspirin with me one day. And it's a pretty big day. It requires a number of steps, but we'll see what we can do to get it done in a single day. So aspirin is this molecule here, C9H8O4. 9 carbons, 8 hydrogens, 4 oxygens. Now to make this, I need two ingredients. One is called salicylic acid, and one is called acetic anhydride. The salicylic acid is the C7H6O3, C7H6O3, and the other one is C4H6O3. So those are my two reactants. And the question was good enough to give me the molar masses without having to figure them out. So otherwise I would have to do 7 carbons plus 6 hydrogens plus 3 oxygens, go to my periodic table, and come up with my molar mass. Same thing with the acetic anhydride. Come up with the molar mass. Now, they've given me the molar mass for ASA also, for the acetyl salicylic acid, which is aspirin. Again, notice I see the word acetyl, which comes from here, and I see the salicylic acid, which is one of my starting ingredients also. Right, so that's what I'm trying to make, and the question is, if I give you so many grams of one reactant and so many grams of the other reactant, how much product can I make? Now notice that I also get another product, which is the acetic acid here, and it's C2H4O2. So before I start, I want to make sure that this is balanced. Right, so I'm going to count my carbons. I've got 7 and 4 is 11 carbons on this side. 9 and 2 is 11 carbons on this side. This is looking good. 6 and 6 is 12 hydrogens. 8 and 4, oh, there's 12 hydrogens. And I have 3 and 3 oxygens at 6. And 4 and 2 oxygens at 6. So it's perfectly balanced already. And notice that it's 1 to 1 to 1 to 1. Right, my balanced equation. Now, if I start by calculating, so I'm going to start setting it up exactly the same way every time. Mass and molar mass, mass and molar mass, mass and molar mass. I'm not worrying about acetic acid. It's going to be there, but it's not really part of the question. So I'm just going to ignore it. Okay, so I won't bother doing all the math because I don't need the math for acetic acid. So let's look first at which one of these is going to run out. Which one is limiting and which one is in excess. So I've calculated my number of moles for both. Mass divided by molar mass, and I'm getting 9,000 moles. And over here, mass divided by molar mass, and I'm getting 14,000 moles. Now to decide which one's going to run out, I need to figure out how many moles of product can I make. So I need to use mole ratios here for my two reactants. So if I do my mole ratio over on this side, number of moles of ASA is equal to, I'm going to start with my salicylic acid and see how many moles of salicylic acid I can make. So I'm going to start with my 9,991 moles of salicylic acid. And then I'm going to use my mole ratio that has 1 mole of salicylic acid for every 1 mole of ASA. 1 mole of ASA, and I have 1 mole of salicylic acid. That's my mole ratio from the question. My salicylic acids cancel, and I get 9,991 moles of ASA. SA. Because remember, the SAs are gone, so I'm left with moles of ASA. How about the acetic anhydride? My number of moles of aspirin, ASA, I think I already know that. Yeah, but I need to look at my other reactant. It's going to be equal to the number of moles, 14990 moles of acetic anhydride times my mole ratio. Mole ratio has ASA on top. Oops. 1 ASA on top and 1 acetic anhydride on the bottom. Right? Again, remember, I have 1 acetic anhydride for every 1 acetic acid from my balanced equation here. One, 4,990. Okay, now notice that change my colors here. Notice that my acetic anhydrides cancel, and I'm left with moles of ASA. Okay, so now the question becomes, which of these two is going to run out first? Well, if I look at the salicylic acid, I have enough salicylic acid to make 9,000 moles of aspirin. I have enough acetic anhydride to make 15,000 moles of aspirin. But one of these is going to run out first. This one's going to run out first. So this is the one that I need to be looking at. Right? This is based upon the number of moles of salicylic acid. Right? So I'm just going to scratch this whole one out because I don't need it. I need to look at the one that's going to run out. So remember, I have two chemicals here. I have the salicylic acid over here. This is the one that's going to be called my limiting reactant. And this one here is my excess reactant. Sometimes I just write it as XS. And this one we usually just write as lim for limiting. So now that I know my number of moles, on this side, 9,991 moles, and I know the molar mass for ASA, I can calculate the mass, little n times big M. So mass, little n times big M. The little n I know is 9,991 moles, and the molar mass was 180.17 grams per mole. Okay, and I'm going to get an answer of, your calculator might give it to you in scientific notation, 1.80 times 10 to the 6 grams, right, which is probably the answer that you will get of aspirin. ASA. So aspirin is a trade name, just like trying to think of something. Kleenex. Kleenex is a trade name. So if you go to the store and you want to buy a box of Kleenex, we often call it Kleenex, right? But if you look for Kleenex in the store, you might find some no-name ones that aren't called Kleenex. Kleenex is actually the brand name, right? And napkins are the word that we often use. All right, so ASA is the chemical name, And aspirin is the trade name. It's one company's name for aspirin. It was the first company to sell aspirin. So most of us still know it as aspirin, but ultimately it's called ASA. Okay, so there's one sample problem. I want to do one more. Let me do one more here. I'm just going to make one up. Let me go back to one of the questions we were doing before. So I'm going to do this question here. I'm going to go with, let me go to a different color pen. Two NH3s plus an H2SO4 makes NH4 2SO4. So there's my equation. Okay, and I'm going to tell you that I'm going to give you 100 grams of each chemical. And I want to know how much ammonium sulfate are we going to make. Now I'll make this a little bit easier for you. I will give you the molar masses. Molar mass for ammonia is 17.04 grams per mole. Molar mass for sulfuric acid is get my periodic table out here. Never too far from a good periodic table. Sulfur is 32 plus, I think, oh, that's not right, 2.02 plus 98.09, and the molar mass for ammonium sulfate is 132.17 grams per mole. Okay, let me just double check that H2SO4. Yeah, 98.09. Okay, so I'm going to start the same way I always do. So again, remember to solve for the mass over here, I need to know the number of moles and the molar mass. Well, I know the molar mass, so I need to find little n down here. So I'm going to start by finding the number of moles on this side and then see which one is going to run out first. So my number of moles here is mass divided by molar mass, right, which is 100 divided by 17.04. I'm getting 5.87 moles. Here, my number of moles is equal to the mass divided by my molar mass, which equals 1.02 moles. Okay. Now I want to figure out how many moles of ammonium sulfate I can get. So my number of moles of ammonium sulfate is equal to, let's start with the NH3 here. Number of moles is 5.07. Of NH3 times my mole ratio. My mole ratio says I have 1 ammonium sulfate, and I have one, oh my, NH3. Okay, again, notice that my NH3s are going to cancel, and I will be left with ammonium sulfate. 5.87 moles of ammonium sulfate. NH42SO4. Let's write the whole thing out. NH42SO4. What about if I use the hydrogen sulfate here? How many moles of ammonium sulfate can I make by using hydrogen sulfate? So if I scroll up a little bit here, I could say my number of moles of ammonium sulfate is equal to the number of moles of hydrogen sulfate times my mole ratio. 1 ammonium sulfate over 1 H2SO4. Again, that's all from my balanced equation. Oh, look at that. I made a mistake here. There's actually 2 ammonias. So actually, let's go back here. I put 1 ammonia down here. I wasn't paying attention, right? Notice that up here I have 2 ammonias for every 1 ammonium sulfate. I should have checked it was balanced. I have 2 nitrogens, 6, 7, 8 hydrogens, 8 hydrogens, SO4, SO4. Okay, so it's balanced now, but I made a mistake when I was doing this. I should have had a 2 down here. Right, and what that does is it changes my answer here to 2.94. moles of ammonium sulfate. Now down here, I'm getting 1.02 moles of hydrogen sulfate. Hydrogen sulfate and hydrogen sulfate cancel, and I'm left with ammonium sulfate. So I'm left with, come on, 1.02 moles of ammonium sulfate, NH4 2SO4. So now I'm going to look for which one's going to run out first, which one is lower. So the NH3s, I've got enough to make almost 3 moles of product. But the H2SO4s, I only have enough to make 1 mole of product. This one's going to run out first, so this is the one that tells me how much product I can make. All right, so again, I'm going to scratch out the one that I don't need, right? And I'm going to stick with the one that I know here, right? 1.02 moles. So now that I know the number of moles, and I know the molar mass, I can calculate my mass. So mass equals little n times big M. Mass equals little n times big M, which equals 1.02 times the big M, which is 132.17. And I'm getting 135 grams of NH4 2SO4 ammonium sulfate. So notice, if I started with 100 grams of each reactant, right, I'm going to get 135 grams of ammonium sulfate. Now, again, you might be saying, hang on, whoa, we learned way back when that all the reactants in a chemical reaction must equal the amount of products, right? Well, it turns out, remember, we just learned up here that there was too much NH3, way more than I needed. So when I was done, if I actually get 135 grams of NH4 2SO4, okay, the question doesn't ask this, but I'll end up with 65 grams of NH3 left over. Remember, it was never used. I had too much NH3. I had way more NH3 than I needed, because the mass of this and this have to equal the mass of the reactants. And remember, I started with 200 grams of reactants, right? 100 grams of one and 100 grams of the other, right? But I only got 135 grams. Means 65 grams of reactant was never used up. I had 200 and I only got 135. That means there's still 65 grams of one of these. Well, the one that was excess. So remember, we said this one was limiting because it's the one that's going to run out, and this one is excess, which means it's going to be left over in the end, right? And I know that I had 65 grams. Now, I would never ask you that, but I'm just thinking, if you're wondering why the mass of the reactants isn't equal to the mass of the products, right, that's the reason why. Okay, so I am going to stop there. I'm going to ask you to try questions 12 and 13 on page 223. Question 12 and 13 on page 223 in the textbook. That's in chapter 6. Okay, so I will stop there. I'm going to send you the link to this YouTube video, and hopefully you get a chance to watch this and do this question on your own, and then we'll go from there. We'll pick up the pieces